Algebraic Structures, Lecture 24, Problem Session. Problem 1. Use reduction modulo A'P and the fact that the algebra of polynomials over a field in one variable is a principal ideal domain for any field to prove Eisenstein's criterion that a polynomial with integer coefficients of the form an x to the power n plus and so on plus a1x plus a0, such that A'P does not divide an, but it divides all other coefficients, and p squared doesn't divide a0, so such a polynomial is irreducible over rationals. Solution. Let us assume that we can write f of x as g of x times h of x. So in particular, the degree of f is equal to the sum of the degrees of g and the degree of h, and we assume that both the degree of g and the degree of h is greater than 0. And of course, we have this decomposition over rational numbers, but we can also assume that it is a decomposition over the integers. Then, when we reduce modulo p, we obtain the following. So the reduction of the left-hand side will be just an times x to the power n, because of our assumptions p divides all the coefficients of our polynomial f of x except for an. And then the polynomial g will have some reduction g tilde, and h will have some reduction h tilde. Since the ring of all polynomials in one variable over the field Zp, this should be P, over the field Zp with P elements is a principal ideal domain, we have in particular a unique decomposition of each element into a product of irreducibles. From this it follows that g tilde must have the form some scalar times x to the power the degree of g, and h tilde must have the form some scalar times x to the power the degree of h. And the scalars u and v are non-zero, so their product is equal to an modulo p, of course. So this means that the constant term of both g and h should be divisible by p, and this contradicts the fact that p squared doesn't divide a0. That's one of the assumptions in our formulation. This proves Eisenstein's criterion. Problem 2. Determine the Galois group for the splitting field of the polynomial x cubed plus 2x plus 2 over the rationals without solving the equation explicitly, and describe the intermediate subfields to the extent that one can without solving the equation explicitly. Solution. Let us denote the splitting field of this polynomial over the rational numbers by capital F. The extension from the rational numbers to f is separable because we are in characteristic 0, and this extension is normal because we defined f as a splitting field of some polynomial. So this means that this extension is a Galois extension. Next, we note that polynomial x cubed plus 2x plus 2 is irreducible over the rational numbers by Eisenstein's criterion, which we can apply for p is equal to 2. So 2 doesn't divide 1, which is the leading term, it divides 0, 2, and 2, and 2 squared doesn't divide 2. So this polynomial is irreducible by Eisenstein's criterion. Since the degree of the polynomial is odd, this polynomial has a real root. Let's call this root a. We don't need it explicitly, but it exists. Next, we note that the derivative of this polynomial is 3x squared plus 2 is absolutely positive. It only has positive values if x is a real number. So this means that this derivative does not have any real roots. And this in turn implies that the original polynomial x cubed plus 2x plus 2 has a unique real root. It can have only 1 or 3 real roots. If it would have 3 real roots, the derivative should vanish at 2 points. The derivative doesn't vanish, so this polynomial has a unique real root. So this means that it has 2 complex roots. Let's denote them by z and z overlined. So overlined means complex conjugation, so we denote by z and z overlined the two complex roots of our polynomial. Then the splitting field of our polynomial is obtained from Q by adjoining these roots A, Z, and Z overlined. Each element of the Galois group defines a permutation of these three roots, and of course is uniquely determined by it because the field F is obtained from Q by adjoining exactly these three roots. This means that we can restrict the element of the Galois group to these three roots, and this gives us an injective homomorphism from our Galois group to the group of permutations of these three roots, which is of course isomorphic to S3. Let's call the image of this injective homomorphism by G. Note that the restriction of the complex conjugation to F is an automorphism of F, of course, so it fixes A and it swaps Z and Z overlined. So this means that our group G contains a transposition which swaps Z and Z overlined. At the same time, we can send a root A of our polynomial to the root zeta of our polynomial, and this extends to an automorphism of F because F is a normal extension, and we use the theorem on extension of homomorphisms. So this automorphism either swaps A and Z, or it sends A to Z and then Z to Z overlined and then Z overlined to A. So it either corresponds to a transposition of A and Z or to a 3-cycle. But we already have a transposition of Z and Z overlined. So if we, in the symmetric group S3, if we have two different transpositions or a transposition and a 3-cycle, they generate the whole group. And this means that our Galois group is isomorphic to S3. So we have already determined that the Galois group of our polynomial is isomorphic to S3. Now, about intermediate subfields, we can use Galois correspondence. Intermediate subfields correspond to subgroups of the Galois group. The group S3 has 6 subgroups. The trivial subgroups, the identity and S3. Then it has 3 subgroups of order 2, where we add to the identity one of 3 elements of order 2. And we have a subgroup of order 3, which contains the identity and the two 3-cycles. That's exactly the subgroup A3 of all even permutations on 3 elements. Now we can use Galois correspondence and describe the intermediate subfield. The intermediate subfield for the identity subgroup is the field F itself. The intermediate subfield for the other extreme case, the group S3, the whole Galois group, is of course the smaller field Q of rational numbers. For the 2-element subgroups, we of course get the 3 subfields which we obtain from Q by adjoining exactly one of our roots. So we can adjoin A to Q, or we can adjoin zeta, or we can adjoin zeta overlined. So we have 3 subfields, and all these 3 subfields have dimension 3 over Q, and 3 is equal to 6, which is the dimension of F over Q, the cardinality of the Galois group, divided by 2, which is the subgroup. The degree of the extension from the small subfield to the subfield of fixed points is equal to the cardinality of the whole Galois group divided by the cardinality of the subgroup. And what remains is the unique subfield L, which corresponds to the 3-element subgroup of the Galois group. So this field L is a quadratic extension of Q because the subgroup has cardinality 3, 6 divided by 3 is 2. And it's a little bit more complicated to determine it. To determine this field, we need to solve the equation explicitly. Note that the naive thing, of course, if we have our 3 roots A, zeta, and zeta overlined, if we add them, this will be an element which is fixed by the 3-cycle. Unfortunately, this element is equal to 0 by Vieta's formula, so the sum of the roots of the polynomial is exactly the coefficient of the next term to the leading term, and in our polynomial that is 0. So this naive approach to find a fixed point generator for the field L doesn't work. So to determine L, one needs to solve the equation explicitly and make some guessings with these explicit roots of our polynomial. So this finishes problem 2. Problem 3. Construct a field with 8 elements and find one irreducible polynomial of degree 3 over such a field. Solution. Of course, we need to write 8 as a power of the prime. So this is 2 to the power 3. So we start with the field Z2. So that's the 2, the prime. And in order to construct a field with 8 elements, we need an irreducible polynomial of degree 3. 3 is the exponent over Z2. Note that a polynomial of degree 3 is irreducible if and only if it doesn't have any roots. So let's try some polynomial. So we take the polynomial x cubed plus x plus 1. Then f of 0 is 1, and f of 1 is 1 plus 1 plus 1 is 1. So this polynomial doesn't have any roots in Z2, which means that it is irreducible. And this means that if we take the polynomial algebra in one variable x over Z2 and factor out the ideal generated by this polynomial, the outcome will be a field with 8 elements. So we denote it by f. And the elements of this field can be identified with polynomials over Z2 of degree at most 1 smaller than our polynomial. So at most 2, which is 3 minus 1. 3 is the degree of our polynomial, we need to subtract 1. And here is a list of all such polynomials: 0, 1, x, x plus 1, x squared plus 1, x squared plus x squared plus x plus 1. It is very easy to write down the table for the addition in this field. It's just addition of the coefficients modulo 2. So that's the whole table. So of course 0 plus anything, we will get that anything. And then 1 plus 0 is 1, 1 plus 1 is 0, 1 plus x is x plus 1, 1 plus x plus 1 is x, and so on. So x plus 1 plus x squared plus 1 is x squared plus x, because 1 and 1 cancel. And in this way we can write down the formulas for addition for any 2 elements in our field. So this is an easy thing, because it's just addition of coefficients modulo 2. It is much more complicated to write down the table of multiplication, because for multiplication we need to use that we take a quotient modulo our polynomial, so x cubed plus x plus 1 is equal to 0 in our field f. In other words, x cubed is equal to x plus 1. Note that plus and minus 1 are the same, because we work over the field with 2 elements originally. Of course, 0 times anything is 0, and 1 times anything is, but then the rest we need to compute. So x times x is x squared. X times x plus 1 is x squared plus x. X times x squared is x cubed, which is x plus 1. X times x squared plus 1 is x cubed plus x, which is 1. And so on. So in each case one needs to write the formula and then use the fact that x cubed is equal to x plus 1 to reduce the expression to one of the elements in our field. So for example, x squared plus x times x squared plus 1 is equal to x plus 1. So here is a complete table for multiplication. Let us note that the multiplicative group of our field has order 7. 0 is not an element there, so everything else but 0. We have 7 elements, and 7 is a prime number, and the multiplicative group is cyclic. So it means that all elements in that multiplicative group, apart from the identity, are generators. So let us try to find some irreducible polynomial of degree 3 over f. And in order to distinguish it, so the elements of our field f are polynomials, so we need to take a different variable. We take variable y. And again, note that irreducibility is equivalent to not having any roots in our field f. So we take the polynomial g of y, which is equal to y cubed plus y plus x. So now x is not a variable, x is now an element of our field with 8 elements. And now one has to compute. So we need to prove, so if you want to check that it is irreducible, we need to prove that it doesn't have any roots. And here one has to insert all 8 elements of our field and check that they are not roots. So if we insert 0 instead of y, of course we will get x, this is not 0. If we insert 1, we will get 1 plus 1 plus x, that's x, not 0. If we insert x, we will get x cubed plus x, so x and x vanish and x cubed becomes x plus 1, that's not 0. If we insert x plus 1 instead of y, we get x plus 1 cubed plus x plus 1 plus x, and then we can rewrite this. If one computes, you will get x squared plus 1, which is not 0. So similarly, g of x squared is x plus 1, which is non-zero. G of x squared plus 1 is 1, which is not 0. And g of x squared plus x is x plus 1, which is not 0. And finally, g of x squared plus x plus 1 is equal to x squared plus x plus 1, which is not 0. So this means that our polynomial doesn't have any roots in our field f, and so it is irreducible over f. Problem 4. Let K inside F be a finite Galois extension. Let P be a prime number dividing the dimension of F over K, the degree of this extension. Show that there is an intermediate subfield L between K and F, such that F has dimension P over L. Solution. Under our assumption, our extension is a Galois extension, so there is a Galois group associated to this extension, and the cardinality of this Galois group is exactly the degree of the extension. And under our assumptions, P divides the cardinality of this Galois group. And this group is a finite group, so by Sylow theorems, G, our Galois group, has a subgroup H with P elements. So there should be a subgroup of order P. And now by the Galois correspondence, if we take the set of fixed points for this subgroup and denote it by L, this will be an intermediate subfield, and the dimension of the bigger field F over this intermediate subfield will be exactly P. And this completes the proof. Problem 5. For a prime P and a positive integer n, denote by f p to the power n the field with p to the power n elements. Show that the algebraic closure of fp is equal to the union over all n greater than or equal to 1 of f p to the power n. Solution. Since for any n the extension from fp to fp to the power n is finite, it's algebraic. So in particular, it follows that each element of f p to the power n is algebraic over fp. This means in particular that the right-hand side of our equality is a subset of the left-hand side. So each element of each fp to the power n is algebraic, so it belongs to the algebraic closure of fp. On the other hand, let f of x be an irreducible polynomial over fp. Then, if we take the polynomial algebra over fp and factor out the ideal generated by f of x, we get a finite field, and hence this field must be isomorphic to some f p to the power n for some n. In fact, n will be the degree of the polynomial f. On the other hand, the extension from fp to fp to the power n is a Galois extension. This is because fp coincides with the field of fixed points for the Frobenius automorphism of fp to the power n, and that the automorphism which sends an element a to the p's power of a. That's a very particular automorphism which exists only in characteristic p. But the fact that this is a Galois extension implies that this extension is normal, and so if our f of x has a root in fp to the power n, it splits over that field. And this means that every algebraic element over fp belongs to some fp to the power n, so the left-hand side of our formula is a subset of the right-hand side. So we have proved inclusions in both directions, and so the left-hand side is really equal to the right-hand side. Problem 6. Let zeta be a primitive third root of unity. Let A1, A2, and A3 be transcendental elements over Q. Define the field K as the field of rational functions in A1, A2, and A3 over the field which is obtained from rational numbers by adjoining our third root of unity zeta. Prove, using the definition, that the equation x cubed minus a1x squared plus a2x minus a3 is equal to 0 is solvable by radicals over k. Solution. Denote by F the splitting field of this equation over k. By Vietta's formula, the solutions T1, T2, and T3 to our equation satisfy the following conditions. So A1 is equal to T1 plus T2 plus T3, A2 is equal to T1, T2 plus T1, T3 plus T2, T3, and A3 is equal to T1, T2, T3. We claim that the elements T1, T2, and T3 are algebraically independent over the field which is obtained from the rationals by adjoining zeta. Indeed, assume that this is not a case. Assume that G is some non-zero polynomial in variables z1, z2, and z3, such that if we insert T1, T2, and T3, we will get 0. Then we can take a product of this polynomial over all elements in S3, and then we permute the variables in the polynomial. So since we take a product over all permutations in S3, we will get a non-zero symmetric polynomial that is equal to 0 when we evaluate it at T1, T2, and T3, because one of the factors evaluates to 0. Now let us recall the principal theorem on symmetric polynomials. If we have the algebra of all polynomials in m variables over some field capital K, and we look at this algebra, then the symmetric group Sm acts on it by permuting the variables. And we can look at the subalgebra of all symmetric polynomials, the polynomials which are not changed by this action. Then the claim of the theorem is that every element, so every polynomial in this algebra of symmetric polynomials, is a polynomial in the so-called elementary symmetric polynomials. We denote them by beta I, so I is between 1 and m, and beta I is defined as a sum of the products alpha R1, alpha R2, and so on, alpha Ri, where R1 is greater than or equal to 1 and is smaller than R2, and so on, smaller than Ri, which is less than or equal to m. We take the sum over all such R1, R2, and so on, Ri. Moreover, these elementary symmetric polynomials are algebraically independent. We can use this theorem to express our symmetric polynomial, which we have here, as a polynomial in S1 and 2 and S3, because S1, S2, and S3 are exactly the elementary symmetric polynomials. And this would imply that these elementary symmetric polynomials are algebraically dependent, and that's a contradiction with this principal theorem on symmetric polynomials. Great, so the solutions to our equation are algebraically independent, and this means that the automorphism group of our splitting field F over K is isomorphic to the symmetric group S3, which acts on F by permuting the solutions T1, T2, and T3. And the group S3 is solvable. In fact, it has the subgroup A3 of all even permutations. That subgroup is cyclic, it has order 3, and the quotient by that normal subgroup of all even permutations is also cyclic, because even permutations have index 2 in all permutations. So the quotient has 2 elements. So we have a cyclic normal subgroup and a cyclic quotient. Also note that our field Q with our zeta attached has both a primitive third root of unity, which is our zeta, and a primitive second root of unity, which is -1. So we can apply Lagrange theorem to conclude that the extension from K to the subfield of fixed points for the subgroup A3 is a radical extension, and the extension from this intermediate subfield to F is also a radical extension. So the extension from K to F is a radical extension, and so by definition our equation is solvable by radicals. And that completes problem 6. Problem 7. Outline the ruler and compass construction of a regular pentagon. Solution. Let us start by noting that 5, which is the number of sides of a regular pentagon, is equal to 2 to the power 2 to the power 1 plus 1, so 5 is a Fermat prime. So by our theorem, which says when we can construct a regular pentagon, for each Fermat prime we can do that, so there should be a ruler and compass construction of a regular pentagon. So this is possible. Now let's explicitly describe how to do this. So the starting point of our procedure, we have 2 points in R2, namely we take the origin and the point 1, 0. That's all we have, and now we are allowed to use an unmarked ruler and a compass. Of course, it would suffice to construct an angle of 72 degrees, because 72 is 360 divided by 5. That's exactly the angle between the origin and the 2 consecutive vertices of a regular pentagon. And if you want to construct an angle, it's enough to construct its tangent or cos or sine. So we will construct cos, and it is very easy to see that cos of 72 degrees is equal to root of 5 minus 1 divided by 4. So starting from the rational number 1, we need to construct the real number root of 5 minus 1 divided by 4. So to construct root of 5, we can draw a rectangle with sides 1 and 2. Note that we can erect perpendiculars using ruler and compass. And the diagonal of this rectangle will be exactly root of 5. And then we can subtract 1 from the root of 5 and divide what we get by 2 twice. Then we will divide by 4. So here is how we do it in practice. So we construct a rectangular with sides 2 and 1. Then the diagonal of this rectangular has length root of 5. And then we can draw here a point because we have length 1, so we can subtract 1. And then using ruler and compass we can divide by 2, so we can divide any segment by 2. We divide by 2 once, we divide by 2 twice, and here we have 1/4 of root of 5 minus 1. That's exactly cos of 72 degrees. And now, if we know what the cos of 72 degrees is, we can do the following. This is our origin, this is 1, 0. So we draw the circle using the compass with the center in the origin and with radius 1. And then on this line, which connects the origin and 1, 0, we can draw the point in the distance cos of 72 degrees and erect the perpendicular at this point. The intersection of this perpendicular and the circle will be the second vertex of our pentagon. And now we can just continue, say, in the counterclockwise direction. This completes problem 7. Additional problems and questions. Problem question 1. Describe the Galois group over Q for the splitting field of the polynomial x to the power 4 minus 9x plus 12. Problem question 2. Find an irreducible polynomial of degree 2 over a field with 16 elements. Problem question 3. Show that the extension from the rational numbers to the rational numbers with the following element adjoint, the 5th root of 1 minus the square root of 3, is a radical extension. Problem question 4. Show that x to the power 6 plus 3x to the power 3 plus 2 is equal to 0 is solvable by radicals over the rational numbers with the primitive third root of unity adjoint. And problem question 5. Outline how to construct, starting from the origin and the point 1, 0, the real number the square root of the square root of 2 divided by 1 minus the square root of 3. So how to construct using the ruler and compass. Thank you very much for the course. This completes the course.